Hello there guys, and welcome back to another epic inexorable maths video. In this video we're going to prove that the area of a circle is πr². Okay, so let's just dive straight into it. First thing you need to know, of course, is that the ratio between the circumference of a circle, that's the same thing as its perimeter, divided by its diameter, is always equal to the number pi, and pi is about 3.14159, and so on and so forth. That's literally the definition of pi. If you didn't know that, that's what pi is. So pi is the amount of times bigger that basically the circumference of a circle is compared to its diameter. Always, for any circle, it doesn't matter how big the circle is. If you rearrange that equation, you get from circumference divided by diameter is pi. You then get circumference is equal to pi times diameter. But what is the diameter? The diameter is always twice the radius. So circumference is equal to 2 pi r, where r is the radius of the circle. And just to be clear, in this circle, we can say this is a radius, or any one of those lines are radii. They're all the same length. Okay, so I've already drawn some stuff down because these shapes are very difficult to draw, so I've just drawn them already. Hope you guys do not mind that. So imagine that you had a circle and you cut it into, say, 8 slices, like a pizza. Okay, that's fine. You could then rearrange those slices if you wanted to, like this, right? There's no reason why you couldn't just do that. You know, just get the slices, put them like that. Fine, no problem. And this length here is r, right? Like this length here, that's r. We can also observe, because that you can clearly see that that's like the length of one of these slices sort of thing. You can also observe that this length here that traverses half of the outside parts, like these are like the crusts of the pizza, right? It covers half of all of them because there are 8 slices, and this is 1, 2, 3, 4 slices of pizzas, the length of the crusts. That means that this must be half the circumference of the pizza. The circumference of the pizza is 2 pi r, so half the circumference of the pizza is pi r. Okay, so this is pi times the radius, and it's the same down here. This is the other 4 slices of pizza going around the outside, so this is also equal to pi r. Okay, and yeah, just to really emphasize that this is one part of sort of the crust part of the pizza. You know, imagine that these 2 slices here are the same slice. There are obviously 4 sort of crusts. I guess you could say if we continue the pizza analogy, there are 4 crusts in half the circumference, so we get pi r. Okay, so that's that shape. Now, why does that, what's the point in doing any of that? Like what's the big deal? Well, imagine that we hypothetically took another circle. So here's another circle. And actually, do you know what? Imagine that it's the exact same circle, okay? Imagine it's the same circle. If I can actually get it to be a circle. There we go. So we're going to pretend that this is the exact same circle with the same radius, the same circumference and all of that. But we're going to cut it up differently. We're going to cut it up into many pieces. Lots of pieces. I'm not going to draw all the slices, but you can get the idea. Imagine that you had a pizza cutter and you literally sliced it into the thinnest pieces that you possibly could. What would the rearrangement of that pizza look like, right? If you rearrange the slices, if you go from here to here, where's the what's the if we sort of arrange the slices like sort of how do you say it? We rearrange the slices so like there's the crust at the bottom, then a crust at the top, like that. If we have lots, let's say you have 1,000 slices, what does that look like? Well, again, it's going to be a pretty rudimentary drawing, but it was, let's sort of go like this, and we'll come like sort of down here like this. This is going to be a disaster, guys, but like just bear with me, okay? Your slices would kind of this is awful, but they'd kind of look like this, right? Like they'd kind of keep going and going and going and going, and because they'd be so thin, okay, just like this. Okay, you get the idea, and that just goes on, okay, until you get to like the last part, and I'll do it at the end. I'll do it at the end just to sort of drive it home. This is, yeah, everything's going crazy. but this is the general idea of what's going on. So, and I'll just fill that one in as well. Okay, so imagine that they're all straight, they're all the same length and stuff like that. Awful drawing, I know, but imagine that that's the case. Well, this length here is still r, right? Because this is the same pizza. It still has a radius of r. Oh my! It still has a radius of r. So it's the same. It's the same length as in the top one as well. Same shape. Okay, and this is still pi times the radius, right? Of course, and so is this length down here. It's still pi times the radius. But what's happening? Because up here, this shape is like, what is this? It looks like a really bad parallelogram, like a really inaccurate one. Because if you wanted to find the radius of the area rather of this shape up here, it would be very challenging because you have all of this excess. You know, you can cut it into triangles. You can say, oh, it's a parallelogram. Look, I'm just going to count sort of the bits that's sort of below and above these crusts. I'm going to get everything in the middle, right? But you have all of this extra space, and how are you going to find the area of that? That's very, very difficult to do. How are you going to find the area of all of these things? Well, you can't really do it. So, if you have less slices, the areas, those little tiny areas that are coming from the top of the crusts of pizza are much smaller. Look at that. Far less area, and you can do it at the bottom as well. It's almost enough to ignore, but it's not enough to ignore just yet though, because the areas are still there. Those tiny little extra areas that just are really getting on us, because wouldn't it be nice if we could make this shape literally be a rectangle, right? We could then just find the area really easily because it's a rectangle. It's almost a rectangle, but it's not quite a rectangle because we have all of this extra stuff going at the top and the bottom. But there is one way to get rid of it. Because right now what we're doing is, if we did pretend that all of these shapes were triangles, we'd have to also pretend that this shape here, which is a circle, we'd have to pretend that it wasn't a circle and that it was actually some sort of polygon, right? So for example, with the 8 slice example, this would be an octagon. So if you did pretend that all of this extra stuff at the top and the bottom was not there, you just did not account for all of this area, then you would actually be finding the area of the octagon instead. You don't want an octagon, you want a circle. But let's say that you have 1,000 slices. You wouldn't be finding the area of an octagon anymore. You would be finding the area of a polygon with 1,000 sides. But what's a circle though? How many sides does a circle have? Well, a circle has an infinite number of sides, or at least you can think of it that way for now. So if you have an infinite number of sides, you need to cut your circle into an infinite number of slices of pizza in order to accurately find the area. But what happens when you slice your circle into an infinite number of slices? What happens to this shape? An infinite number of slices, not lots and lots, infinitely many. Okay, what does that turn into? It turns into nothing other than a perfect rectangle. Okay, we have literally cut it into an infinite number of slices, and again, it's not possible to draw it, but just trying to visualize it, the thinnest slices that can exist. There are an infinite number of them. Now, again, I can't draw this, but if you really could draw it, if you could really visualize it, what would the extra, from the ones up here, all of this extra area, what would all of this extra area look like for that? Well, if there were really truly an infinite number of slices, then all of those tiny little slices would not be segments of a circle anymore. No. They would be triangles. They would be perfect triangles. And therefore, there would not be any area at all that's not accounted for in the little crusts of the circle. You truly would just have a series of triangles that you can sort of just group together like this. Triangles. Not slices of pizza, not segments of a circle or sectors of a circle. No. true triangles. And this genuinely does become a rectangle. It still has a length here of pi r. That hasn't changed. It still has a radius of r. That hasn't changed. But the way that you find the area of this shape now is very, very trivial. It's literally just length times width because it's a rectangle. And if we do length times width, we get pi r times r, right? Pi r is the length and r is the width. Pi r times r, that's equal to pi r squared. And that is then the area of a circle, okay? The area of a circle, we have proven, is pi r squared. Thank you guys so much for watching. Highly appreciate it. And I'll see you in the next video. Cheers.